Hello out there and welcome to Peter's online tutor. Today we shall be looking at physics. Now we're still going to continue the series on half-life. So we are looking at half-life part 2. Now there's a question on the board for us. It reads, a radioactive substance of mass 768 gram has a half-life of 3 years. After how many years does this substance leave only 6 gram undecayed? Okay, now let us go on. Solution. Now, I gave us a simple formula the last time we talked about half-life part 1. Okay, so I'm still going to be applying the same formula here. All right. Now, we said N is equal to big T all over T half-life. Okay. Now, recall that N stands for the number of of the radioactive substance. All right. Now, the big T here, represents the time. Okay. And then this T half here represents the half-life. Okay. Now, I also gave us this fraction remaining. Okay. And then I said fraction remaining is given as 1 over 2 raised to the power of Of n. Okay. Now, but if you look at this, we are having the initial mass. Okay. The initial mass of the radioactive substance. So, initial mass. Okay, that is capital letter M. Now we have it as 768 gram. Okay, now by the time the radioactive substance has undergone some process of decay. Okay, so we are left with 6 gram. Okay, so the final mass that is small letter m equals 6 gram. All right, so let us see how do we bring in that particular formula, because we are asked to find after how many years does this substance leave only 6 gram undecayed. So what are we asked to find here? We're asked to find our big T, because our half-life here is given to us as 3 years. Is that clear? So from here now, what do we do? Okay, what can we do here? Now, if we look at this, mass of substance, okay, that remain undecayed, okay, all right, is given as small m, okay, that's the final mass is equal to capital letter M, brackets open, the fraction remaining. Please take note of this. All right, so this is what we shall be using to get the value of our m. All right, now this our m here is 6. Okay, now this other big m here is our 768. Okay, now brackets open, 1 over 2 raised to the power of n. All right, now we shall be dividing both sides by 768. Okay, both sides by 768. This cancels this. Now, 6 here, 1, 6 here is 128. Okay, so we shall be having at the end of the day 1 over 128 equals 1 over 2 raised to the power of n. Is that clear? So at this point, we can easily cross multiply. Okay, so this times 1 becomes 2 raised to the power of n, and then this times 1 becomes 128. Is that understood? All right, so from here, I'll be having 2 raised to the power n equals. Now, how many times can 2 go in 128? 128, 7 times. Okay, 2 raised to the power of 7. Is that clear? So from here, I can easily strike out 2. So what is my n? My n at the end of the day. So from here, my n now is given to us as As 7. So that is the number of Of radioactive substance. All right. Now, having gotten our n, we can now use this to get the time. Is that clear? So from here, our n is equals to big T, and this is the half-life. All right. Now, our n now, that is the radioactive the number of radioactive substance is equal to 7. Okay. So we are looking for the number of years that the substance remain undecayed. That's our big T. Okay. So this is our T, we are looking for it. And then our half-life is given to us as as 3 from the question. Okay, so that is the value of the half-life. That's 3 years. So at this point, we can easily cross multiply. So t times 1 is t, then 7 times 3 is 21 years. Okay, 21 years. So the number of years that it's actually take this radioactive substance, okay, to remain undecayed is what is 21 years. All right. So if you love what you have seen so far, kindly click on the subscription button, like, share, and comment on this video. Thank you.